In this video, I'm going to continue looking at the hydrogen atom. So in the previous video, we ended up getting this formula that I have at the top right here, which is the Bohr formula. And we can see if we put a 1 in for this n here, and then substitute all the constants in this part here for the known constants. We have the Planck constant, the mass of an electron, the charge of an electron, pi, and the permittivity of free space. So this will just become 1 right here, and all we're doing is just putting in these constants here, and that gives us an E1 equal to minus 13.6 electron volts, and that's the energy needed to ionize the hydrogen. And then so if we want to, and so that's to ionize the electron from the ground state of hydrogen. So if we want to get the wave function for the ground state, so first what we're going to look at, so this is the wave function solution right here. We have our radial part right there and our spherical harmonics right there. And so I have right here, circled in red, this came from quite a few videos, well, not that many, but a few videos back when I was talking about the infinite spherical potential, and we just kind of made this substitution where we took our radial function here and did this u as a function of r over r. And if you remember from the first video on the hydrogen atom, we had this u this u as a function of rho, where if you remember rho is equal to our kappa r, so it's equivalent to r, and we ended up with this right here, where we have our u as a function of rho being equal to this rho to the power of L plus 1 times e to the power of minus rho times this v that's a function of rho. And as I've said, this v as a function of rho, we're going to find out is going to be the associated Laguerre polynomials. So if we bring these two things together, so I'll bring it together, red, blue is brought together as purple, so this purple right here, this is our radial part of the solution here. That's equal to the u r over r, which if we then substitute this this in for the u, we have 1 over r times the rho to the L plus 1 times e to the minus rho times our v as a function of rho. And remember, rho, as I said, or v as a function of rho, is a polynomial, which, as we'll see, will be the Laguerre polynomials. And the coefficients of that polynomial are found by this recursion formula here. But we also saw in our last video that rho is equal to r over an, and so if we make that substitution, we end up with this right here. And so this is sort of the radial function that we're going to be working with here. And so if we try to solve for if we go up here, if we try to solve for n equals 1, then our L has to be equal to 0, and this right here, the J plus 1, is going to be equal to 0. So all we have is our C sub naught. And what we will find is we have our R where n is equal to 1, L is equal to 0. So that's not a 10, that's a 1 and then a 0. And that is going to be equal to, so we have our 1 over R, and that is times R over A, then n is equal to 1, so we'll just call that R over A, and that is raised to the L plus 1, where L is equal to 0, so it's just a 1. And then we have our E to the minus, and now we know that R over A, because our n is just equal to 1. And then our v function of rho here is just going to be the c sub naught, because remember it's c sub naught plus c1x plus c2x2, so on and so forth. But we said that everything after c sub naught is 0, so those are all canceled out, so we just end up with c sub naught. And so now we can do some canceling out. So this r cancels out with that r right there. And so what we have is c sub naught over a times e to the minus r over a. And so this is our solution to the radial part of the equation, but we have to normalize this. And so to do that, what we're going to do is use, we're going to use this. So we have our integral from 0 to infinity of our r1 0 squared r squared dr is equal to our c sub naught over a, and these are both also squared, so square integral from 0 to infinity of e to the minus 2r over a, because it is squared, r squared dr, and that will be equal to c sub naught squared a over 4 equals 1. And so what we end up with is that our c sub naught is equal to 2 over the square root of a, because we have all this, and we are dividing both sides by a and multiplying both sides by 4, and then taking the square root of all of this part right here. And so we end up with well, and in the Griffiths, he also says that our spherical harmonics, and I've talked about the spherical harmonics before, for L equals 0, which also means M is going to be equal to 0, is 1 over the square root of 4 pi. And so our full wave function for n equals 1, L equals 0, M equals 0, which is a function of r, theta, and phi, is going to be equal to, our wave function is equal to 2 over the square root of a, that was our c naught, and then we had from our equation up here 1 over a, so we have 1 over a, and then we actually get from the spherical harmonics, we actually get a 1 over the square root of 4 pi. So that comes from our spherical harmonics. And then we still have our e to the minus r over a. So e to the minus r over a. And so now we can do a little bit of simplifying. So we can bring this 4 outside of the square root and cancel it with that 2. We can sort of put a square here and make that the square root so that we can turn this into a 1 over a cube square root. And then of course this pi is under a square root. And so we have 1 over a cube, 1 over the square root of a cube pi e to the minus r over a. And I will write this again right here to make it a little bit clearer. So we have equals, we have a cube pi square root 1 over that, and then our e to the minus r over a. And so this is our solution to the wave function for the hydrogen atom at the ground state. And so we can do this for other states as well. And so if we want to go to n equals 2, so if we go to n equals 2, so the first thing is what we will find is that if we go back to here and put an n equals 2 right here, this obviously becomes 4. And so we have minus 13.6 divided by 4. And so E2 is equal to minus 13.6 divided by 4. And so that is equal to minus 3.40 electron volts. And so that is the ionization energy, or the binding energy of an electron in a hydrogen atom at the next level up from ground state. And so then if we do our recursion formula for this next state, what we find again is that we have our C naught as the first part of our polynomial. So we have our C naught, and then the next part, so remember, it's going to be, C1x sort of form. But what we do if we plug all that into this is that we end up with minus C naught. And so if we put our C naught into here with n being equal to 2, we end up with C naught, and then that is times our x. And remember, in this instance, our x is our rho, so we end up with this, which we can then distribute that out. So 1 minus rho, so we have C naught times 1 minus rho. And if we plug that then into our equation, which remember was this right here, what we end up with then, so if we have our radial equation for R2, and we with L equals 0, and remember in this one we'll be able to have L equals 1 as well, and that will give us something a little bit different. So we have our C naught over 2a, then we have our 1 minus, and then I'm going to substitute in the r over na for our rho. So that's r over 2, because remember n is equal to 2, so 2a. Then we have our e to the minus r over na with n being 2, so n or r over 2a, like that. And if we then do this for the r with n equals 2 and L equals 1, what you'll find is that we end up with C naught over 4a squared r times e to the minus r over 2a. And so this is what we end up with when we set n equal to 2, which allows us to have L range from 0 to 1, because L always could be anywhere from 0 to n minus 1. And so these are the two solutions to the radial part of the equation for our Schrodinger equation of a hydrogen atom. And so, I mean, you could keep doing this with higher and higher n, and if we had n equals 3, then L could be 0, 1, and 2. And when we look at the spherical harmonics, which also is the m can be anywhere from minus L to positive L, going in integer steps. And so those are our quantum numbers. And so down here, I just once again took pictures right out of the book. And so this is saying, so this is coming right after all the stuff I was just talking about in the book. And this is for arbitrary n, the possible values of L consistent with, so with an equation earlier on in the book. And let me flip here. That was our small n defined as big N plus L. L being equal to 0, 1, 2, all the way up to n minus 1, as I just said. For each L, there are 2 L plus 1 values of m, because there is going to be the zero, so m equals 0, which is kind of the plus 1 on there. That's why we add a plus 1. But then it's plus and minus, 1 plus and minus 2, all the way up to plus and minus L. And so this part right here gives us the 2L, and then this is the plus 1, because we have that extra 0 there. And that's why we end up with being able to have 2L plus 1, which is equal to our n squared here. And so then this goes on to say that the polynomial of v rho, defined by the recursion formula, is a function well known to applied mathematics, and it is this right here, where the L PQ is equal to this, which is the generating function, and this is the associated Laguerre polynomial, where we are using the qth Laguerre polynomial. And so over here, this table on the top are some of the Laguerre polynomials. Then down here are some of the associated Laguerre polynomials. And I've talked about more in my differential equations playlist about how we actually obtain these things. So if you're interested in a little bit more detail on that, then you can watch those videos. But essentially, what it's doing is, remember, we had our solution was our u, which was a function of rho, was equal to our rho to the L plus 1, and then our e to the minus rho. Then we had that v that was a function of rho there, and that is our Laguerre polynomials. So that was our Laguerre polynomials, and we can put that as a function of rho, which, remember, rho was equal to kr, and our r is sort of our independent variable, so you could even say that r is sort of equivalent to x. And so we see that this is using x in here, but we can see how that is related to our rho, which is the rho being the distance from the nucleus of the atom. So rho is equivalent to our distance from the nucleus of the atom. And so this is a function over space, uh, going from the center of the atom. And so we can actually see that. I think I forgot to put those on here. I have the pictures here, and so this is the wave functions. But we can see here, so this is the graphs of the hydrogen radial wave function. So these are from our Laguerre polynomials. And we can see that we end up with these, so 0 here would be the nucleus of the atom. And then we are going out here, which is our distance from the nucleus of the atom. And so we can see our wave function starts off large. So if we have our 1, 0 here, we see that it just kind of goes down and then sort of asymptotes towards 0, which is what we would expect from our s orbitals. And so if we look here, so these are some of the hydrogen wave functions. So this doesn't show the s1 orbitals, but we can see the s2 orbital here where our n is equal to 2, and that is this right here. So we see that goes down. We have this node here where it crosses the x-axis, where it's 0, and then we go down into this sort of, I guess, negative amplitude here. And this goes back to why we use the Born rule of squaring this so that we end up with all positive probabilities here, because a negative probability doesn't have any real physical meaning. But we see this goes down to negative, where if we squared that, it would go to positive, and so we'd have this sort of two-lobed thing here, and that is what we get from this right here. And so you can see it for different values. So 1, 2, 3 with L being 0. Then we have 3, 1. And if we look at 2, 1 right here, you see this has a node right at the origin, at the nucleus. Wow, hit a kind of a brain fart. But we see we have this lobe kind of going up like this and then asymptoting down. And so that is like our p orbitals. So this has the 3, 1 p orbital here, which would be this one right here. So we see that has a lobe that goes up, it goes down, it crosses the x-axis here, it goes to 0 and then goes down to this negative here. And that is our p orbital that looks like this. And we see that we have nodes that go like this, and that would actually come from the spherical harmonic part of the wave function solution. Yeah, so this is this right here. So these are the first few radial wave functions for the hydrogen atom here. That's combining our associated Laguerre polynomials with our rho to the power of L plus 1 times e to the minus rho, and this is just substituting r over na for rho, and so that's why we end up with with this e to the minus r over 2a, because that's n equals 2. That's where the 2 comes from. We have our r over a, and then the 2 here from our n. And so this is, pretty much what we were just looking at. Right here, this is our sort of full solution, our full wave function solution right here. And so we have this normalization factor here, which I believe came from, no, this is the, right here, this is the factor that comes from our our generating function, or our recursion formula right here. And then we have our e to the minus r over na. We have this is our rho to the L essentially right here. Then we see in this square brackets over here, these are our associated Laguerre polynomials. And then this y, what is a function of theta and phi right here, this is our spherical harmonics. And so we have this normalization. Well, this shows that the wave functions are mutually orthogonal right here. But essentially, as we were going through all of these videos, this right here in the box is what we were trying to get. As I said, while doing the hydrogen atom, I was only looking at solutions to the radial part of the equation because the spherical harmonics are the same ones that we were able to use from the infinite spherical potential. So if you want to see more about the actual spherical harmonics, I would suggest watching my videos on the infinite spherical potential, which are the couple of videos that came before these hydrogen atom orbital videos. And so, yeah, like I said, this is sort of what we were trying to get to here. We have this stuff which comes from our radial part of the equation, this square root of 2 over na cubed. So all of this, which is sort of a factor that normalizes this. And then we have our e to the r over na, which is that exponential part. And then we have this 2r over na, which was that sort of rho to the L plus 1 part. And then we have our associated Laguerre polynomials. And then we have our spherical harmonics. And this is in that that form where we have done the separation of variables. So the separation of the r variable, which is the radial part, so distance from the nucleus of our hydrogen atom, and then the spherical harmonics, which is sort of what the wave function is doing at every sort of, I guess, given shell of a certain distance in all directions from the nucleus of the hydrogen atom. I think I might make another video just to sort of sum up all this stuff with the spherical harmonics and the radial equation, just to sort of, I think, give the intuition now that we are sort of coming out of all of the being bogged down in a lot of the mathematics here. But anyway, I hope you found this video useful, and I will see you in the next video.